Hello everyone, today we're going to be doing a quick overview of the various chemistry disciplines. So for most of you, this should be essentially old hat. So I'm going to go ahead and try and walk through the major subdisciplines of chemistry and how these can be kind of subdivided and how they kind of lend a different perspective to how we look at chemistry. So as many of you know, chemistry is typically broken up into 5 major branches. Organic, inorganic, analytical, physical, and biochemistry. And each one of these gives us a very different view of the world. Each one tends to look at the world through a different lens, and that different lens tends to bias how we think about the world. However, it is worth noting that each one of our chemical topics can often be viewed through at least 2, sometimes through all 5 different lenses. And so oftentimes figuring out which branch of chemistry you're most interested in is not only just a matter of what topics you care about, but how you like to look at the world. And this can give you some very important ideas of how you want to go ahead and move after you finish at Truman. Because if you're more of an organic chemist, you're going to want to tend to get certain jobs or do certain things. Whereas if you're like me and a physical chemist, you're going to want to be constantly asking the question why and want to choose a job that orients around that idea. But it is worth noting that increasingly, most of the coolest parts of chemistry aren't just focused in on each one of these subdisciplines. They're at the intersection areas because pretty much most of the interesting organic chemistry questions that are just organic chemistry have already been answered. Similar with the other disciplines, where a lot of the new knowledge and progress is being made is at these kind of interaction zones. So if you're interested in one of these interaction topics, trying to figure out how you want to approach it can be a very important question for the future. So let's start with the topic you're probably the most familiar with right now because you're probably sitting in the class. Organic chemistry. So as we probably taught you in Gen Chem, organic chemistry is pretty much just a way to talk about anything that is a carbon-rich compound. So let's ignore the metals and just focus in on the things that contain carbon. So this is going to be very commonly used in a lot of chemical industries, including petrochemical, which is just taking long carbon chains and turning them into things I can actually sell. Polymer chemistry, which is often taking those petrochemicals, but occasionally agrochemicals, and turning them into plastics or other useful polymers. But we also have the classic pharmaceutical industry. So these are often the big money earners in terms of chemistry, and so get a lot of the attention. But there's a huge range of other types of applications of organic chemistry, including specialized solvents and other such things. But usually when people are talking about organic chemistry, you're looking at one of the big 3. However, one of the things that's important to remember about organic chemists is what lens they tend to look at the world through. So they often see the world as a series of reactions. So how do I go ahead and take a cheap precursor, it may be botanical, and turn it into something I can sell? And the answer is usually a long chain of reactions. So a lot of organic chemistry is focused on one of 2 major processes. First, how can I develop new chemical reactions that may let me make a new functional group or allow for a new functionalization of an old molecule? Preferably something that works under better conditions, cheaper, a lot of these things that industry loves. The other option is what's often called total synthesis. So you go ahead and you go into big textbooks of previously known reactions, and you figure out how you can pair them together to go from a cheap starting material to something you can sell. So this is often the lens that organic chemistry is looking at, is these 2 questions: new reactions and total synthesis. However, it turns out the world is not just made of carbon. And that brings us to inorganic chemistry. So this often is going to go anything from simple inorganic compounds, such as carbonates and CO2, to reagents such as borohydrides, but it's also going to include organometallics. So this is where I have a metal center surrounded by a whole bunch of organic linkers. But it goes all the way up to materials chemistry. So this would be things such as looking at alloys and metals and nanomaterials. So again, most of you should be familiar with the ideas of simple inorganics from general chemistry. However, the details can get quite interesting. However, organometallics are typically going to be used for things like catalysts. And this is one of the reasons why a lot of money is spent on inorganic chemistry, because we're always in search of new catalysts. And organometallic compounds are beautifully suited for it, because you can take a previously known catalyst and then treat it like a tinker toy, pull off a ligand, put on a new one, and try and tailor the new set of chemical behaviors. And this general idea also makes organometallics quite useful for any number of other processes, such as photosensitizers, or dyes, or stabilizing agents. So essentially things where I might want to be able to systematically and slowly adjust behavior. Organometallics are great for this. However, we can also again extend our organic catalysis, or organic chemistry, to materials chemistry. So this includes things such as our good old friends metals and alloys, and even ores. So these are going to be a lot of compounds and species that don't contain any carbon, but often are very interesting, may have a lot of very cool behaviors. And also includes things like ceramics, silicon agents. So a lot of this materials chemistry has become really popular in recent years. But again, because inorganic chemistry is almost defined as anything that isn't organic, the number of topics are quite endless. So inorganic chemistry tends to attract two major sorts of people. So it tends to be people who like chemical reactions and are sick and tired of white powders, so they love the colors that you get from a lot of inorganic compounds. But they also also tend to include a lot of people who like these chemical reactions and materials of organic chemistry, but want to work with much cooler materials. So again, this can include nanomaterials, surface chemistry, metal organic frameworks, which is essentially just a series of metal centers linked together by organic linkers. So it's like the old toy Connects, and they're very cool. So there's almost always a lot more you can do with inorganic chemistry, just due to the sheer range of topics. But it often is a lot more complicated and can be a lot trickier. However, while organic and inorganic chemistry tend to be mostly focused in on what types of materials and chemicals you study, once you get into analytical chemistry, it's a lot more about what procedure you use. So analytical chemistry should appeal to anybody who likes to know exactly what they're working with and exactly what a species contains. So if you like making chemical measurements, if you love spending time on a spec, analytical chemistry is for you. So whereas where analytical chemistry really shines is it's the eyes of the chemistry. So if you've got a sample and you want to know exactly what's in it, which is needed before you can answer almost any other question, you need to be a pretty good analytical chemist. And as a consequence, if no matter what type of chemistry you do, as long as you're not a theoretical chemist, you're probably going to need to be a pretty decent analytical chemist. But there also means that there's a huge call for analytical chemists in industry, because anytime you do quality control and analysis, often called QA/QC, you're going to need a good analytical chemist. So if you like working in industry and you like working with your hands and you enjoy making measurements, analytical chemistry is a great subdiscipline. But again, it isn't just going to be, say, working with industry for, say, analyzing how pure a product is. It can also include things like medical testing, which is really relevant now in the age of COVID, as you often need a good analytical chemist to be able to exactly know what your tests are telling you. But it's also become very popular in things like water quality. So a lot of water treatment plants need to have a couple analytical chemists on hand just to make sure the water that they treated is safe and the water that's in the drinking in your drinking fountain is also safe. So analytical chemists tend to do a lot of the backbone work of chemistry. And again, is a really important subdiscipline to know, even if you decide to go into a different topic. Now that brings us to physical chemistry. While analytical chemistry cares a lot about what we have, physical chemistry focuses more on the question of why. So no matter what you're doing, if you keep asking yourself why, so why did this chemical reaction occur? Why am I absorbing photons? Why do I get this signal? You're essentially getting into the idea of physical chemistry. So again, physical chemistry is a little bit of an interesting subdiscipline because it tends to overlap the most with all of the other disciplines. If you're trying to really get into the question of why something happens and explaining your results, you're slowly approaching physical chemistry. So again, it's often thought of as more or less Gen Chem on steroids, as we're just focusing a lot on the questions of why do what we teach you in Gen Chem break down, and how can I improve my model of reality? So if you really like answering these why questions, I highly encourage you to spend some time in physical chemistry. But it is worth noting that there is some chemical topics that are almost exclusively the domain of physical chemistry. And these often include things that are inherently thermodynamical, so involve the flow of energy or materials. So this is a lot of things like fluid dynamics, flow chemistry, heat dissipation, and things that are inherently quantum mechanical in nature. So this includes a lot of laser work, a lot of photodynamics. Anything where we're watching electrons or photons tend to flow tends to dominate with quantum mechanics. And because of the complication of these topics, they're often kind of suborned into physical chemistry. But this also means that physical chemistry tends to have a dominant role in areas where these topics tend to appear a lot. So a lot of energy chemistry and a lot of materials and surface chemistry, where these topics tend to dominate. But also because of this, it means that physical chemistry tends to have the greatest overlap with chemical engineering, more than the other four disciplines. So if you really are interested in a lot of materials or chemical engineering topics, physical chemistry is a great place to start. And this leaves us to the new kid on the block of chemistry disciplines, and that's biochemistry. So biochemistry is more or less taking one of our other four disciplines and then just focusing exclusively on the study of molecules that occur in biological systems. And it tends to focus a lot more on the biological process side than just the simple molecule side. But because of this, you can find a little bit of the other four disciplines sitting in biochemistry. So this can go anywhere from the organic chemistry of small biomolecules like biomessengers. It can also include inorganic chemistry like metal-containing active sites in proteins, and a lot of analytical chemistry because you need to measure everything, and a lot of physical chemistry because you need to know why it's happening. But there's also some topics that are just more unique to biochemistry, such as a lot of molecular biology and genetics to help control how pathways proceed. And it also is worth noting that biochemistry even is an important discipline, even if you don't go into biochemistry, because it's really important to kind of see how chemical systems work in biological environments. And with the advent of a lot of biomimetic chemistry, so trying to take ideas that work in biology and try and make it so that humans can reproduce that idea, can be very important. And while I originally graduated as a biochemist and haven't worked on biochemistry since, I've tried to do a lot of biomimetic work for which understanding enzymatic behaviors have been really important, and it's worth acknowledging that. And it's also worth noting that a lot of biochemistry has also become increasingly important in recent years as we've tried to move away from expensive things like organometallic catalysts and trying to move things to things such as bioreactors, because why design an expensive iridium containing catalyst when I can make yeast do the job for me? And in addition, with a lot of money for chemistry going to medicinal chemistry, it's very important to have a good background in biochem, because don't be afraid to go where the funding goes. So this gives us our 5 major disciplines in chemistry, but there's almost an infinite list of sub-disciplines, um, which are often combined by the overlapping areas of kind of our major chemistry disciplines. And it's worth noting that it's possible to approach a lot of these disciplines from multiple different perspectives. For example, if you're interested in agrochemistry, you can either do this from a classic organic background, whereas say, how do I go ahead and make a new herbicide, but you can also approach this from a biochemical perspective of essentially what enzymatic paths in my insects am I trying to attack. But there can often be a little bit of inorganic chemistry, such as if you're trying to work on fertilizers, and a lot of it analytical chemistry. So while I'm giving you a good general list of a lot of sub-disciplines, it's worth noting that when I'm assigning them to various disciplines, you can approach almost any of these categories from almost any of the disciplines. And it's also worth noting that you don't have to just choose one sub-discipline to study. I originally trained as a theoretical chemist and am a bit of a physical chemist. But turns out I've studied environmental chemistry, electrochemistry, mechanistic analysis, chemical engineering, a lot of materials chemistry, and organometallic chemistry. So you can do a lot of different work, and one of the big goals of your undergraduate and graduate career should be trying to get you exposed to as many sub-disciplines as possible so you figure out what you really enjoy. So I hope that you go ahead and think about which one of these topics sounds the most interesting to you before our next class, where we try and talk about what you want to do with your chemistry degree. Until then, take care.